Here we have what we call a polynomial inequality that we want to solve. So we want to know when the polynomial x plus 2 times x minus 1 squared is greater than 0. So for a polynomial function, it could switch from being above to below or below to above the x-axis only when we have a horizontal intercept. So the first thing that we want to do is find any horizontal intercepts of our function. So the way that we find a horizontal intercept is by taking our function, so taking x plus 2 times x minus 1 squared and setting it equal to 0, solving for x. So since it's already in factored form, we take each factor and set it equal to 0. So we get x equals negative 2, and x equals 1. So these are the zeros of our function, and these would be the x coordinates of our horizontal intercepts. Now let's think about the long-run behavior of the graph. What kind of shape do we have with our graph? So since we have one factor of x plus 2 and two factors of x minus 1, we have a total degree here of 3. There's 3 factors altogether. If we were to multiply those out, we would have an x to the third power. And our leading coefficient here is just 1. So we have an odd degree and a positive leading coefficient. So when we have odd and positive, the left tail is going to go down and the right tail is going to go up using our rules for long-run behavior from a previous section. So using this information, let's look at how we could sketch our graph. So I'm going to draw just in my horizontal axis, and I'm going to mark negative 2 and positive 1. So one additional piece of information that we can use from our factors, because the factor of x plus 2 had an exponent of just 1, it has an odd exponent, we know that it's going to cross the x-axis at negative 2. But the factor of x minus 1 has an exponent of 2, an even exponent, which means the graph will just touch the x-axis there, but not cross, or kind of bounce, you could almost think of it. So if I mark in those horizontal intercepts at negative 2, 0, and 1, 0, we know that the left tail has to be going down from our long-run behavior. So if it's going to touch at 1, it must come up and then just touch, and then we need our right tail to end going up. You can confirm this shape by taking a look either in Desmos with your graphing calculator. We just need a rough sketch of the graph to help us think about where is it above and where is it below. So using our sketch of our graph, now look back at the original problem. We want to know where is this polynomial function greater than 0. Greater than 0, another way to say this is we're trying to find where is it above the x-axis. So our graph has been divided into 3 sections. So in kind of section number 1 here, the part to the left of negative 2, our graph is down below the x-axis. Here in the middle in section number 2, it's up above the x-axis. And here in section number 3, it's also up above. So we're interested in those parts that are above. So in between negative 2 and 1, it's above. And from 1 forever off to the right to 1 to infinity, it's up above. Because this inequality did not include the option for equal to 0, we do not want to include where we have our x-intercepts, our horizontal intercepts marked with the red dots, are not part of the solution. So we want the part shaded in green, but not the red dots. So in interval notation, the way we can write then the solution to that inequality is from negative 2 to 1, and then we have to skip that red dot, and then from 1 to infinity. So when you have a polynomial inequality, your first step is to find your horizontal intercepts, because these are the potential places for where your graph could switch from above to below or vice versa. Find your horizontal intercepts and then determine the long-run behavior of the function to help you sketch the graph. You can also use technology to help with this. Sketch a rough picture of the graph and then mark where is the graph above and below the x-axis. I use arrows just to help me keep track of that. And then decide which of those sections are the solution you're looking for. Greater than 0 will be above, less than 0 will be below. So here, since we wanted above, sections 2 and 3 on our graph are both above, so both of those are in an interval notation as part of our solution set.